Today we want to look at molecular luminescence spectroscopy. Luminescent electronic processes. So how define luminescence? The radiation produced by a chemical reaction or internal electronic process, possibly following absorption. So some of these types of luminescence include fluorescence, we have phosphorescence, and chemiluminescence. So for the case of fluorescence, absorption of radiation to an excited state is followed by emission of radiation to a lower state of the same multiplicity. That is very important. It can occur about 10 raised to power 5 to 10 raised to power 8 seconds after photon absorption. Then phosphorescence is absorption of radiation to an excited state followed by emission of radiation to a lower state of different multiplicity. So the key difference there is the multiplicity. So for fluorescence it is to the same multiplicity, but for phosphorescence the emission of radiation to a lower state of different multiplicity. And one thing you will realize that for fluorescence it occurs 10 to 10 raised to power 5 seconds after photon absorption. So that tells you that phosphorescence takes a bit of time to take place. Then a bit of history of phosphorescence spectroscopy. In 1845, Herschel first observed blue fluorescence from a quinine solution excited by sunlight. Then 1852, Stokes first explained fluorescence in quinine as arising from frequency differences in light. In the 19th, Jablonski developed theory of excited state processes and anisotropy. In 1950s, first fluorescence spectrometers developed at NHI. Molecular fluorescence is non-resonant fluorescence, which is a phenomenon in which absorption of light of a given wavelength by fluorescent molecules is followed by emission of light at a longer wavelength. Why use fluorescence? It's a complementary method where if you compare fluorescence and UVVs, you realize that mass detection limit for fluorescence is even lower. It can be able to detect even lower. It is very sensitive method. Even if you check the concentration detection limit, it can be able to detect lower compared to UVVs. So it's a sensitive method. It's very sensitive, and compared to UVVs, which is a universal method. So the spins here are unpaired, and this one in the singlet state, the spin are paired. Then so this is a typical Jablonski diagram where we have this occurrence of luminescence. So if you look at this fluorescence and this for phosphorescence, So you will realize that phosphorescence is occurring a bit later through a process called quenching. So if you look at this diagram, there is what we call internal conversion, then there is internal crossing, then we have fluorescence. So maybe we will need another time to just discuss more on Jablonski diagram. But when you see the word S2, if you see the word S2, like here you have S2, we call it S2 and S1, they are just singlet states. Then T1 are just triplet states. Then fluorescence is a singlet to singlet state process, and phosphorescence converts from singlet to triplet state via intersystem crossing. That's where, when you are defining fluorescence, we say that it leads to change in multiplicity, and it leads to no change in multiplicity. But for phosphorescence, there was change in multiplicity, because it is there's a conversion from singlet state to multiplet or triplet state. So excitation directly to a triplet state is forbidden by selection rules. That when I think you know selection rules is always forbade change from singlet to triplet state. Then some of the terminologies we'll encounter in chemiluminescence spectroscopy. We have what we call quantum yield. It's just the ratio of molecules that luminescence to the total of molecules, to the totals of molecules. So quantum yield. So if you have it's just a ratio. So if all of them are going through luminescence, then it means we have 100%. But of course, that is not always the case. Then we have resonance fluorescence. Fluorescence in which the emitted radiation has the same wavelength as the excited radiation. So that is what we call resonance. Resonance, same wavelength. Then we have internal conversion. So after absorption of the photon, molecules in condensed phases often relax to a lowest vibrational level of S1 within 10 raised to power negative 12 seconds. So that is what we call internal conversion. It's just the process where after photons, after molecules absorb photon, they always relax to the lowest vibrational level of S1. Then intersystem crossing is a transition in which the spin of the electron is reversed, where we have now change in multiplicity in molecules. We have it from singlet to triplet. We have dissociation, excitation to vibrational state with sufficient energy to break a chemical bond. Just an excitation. Dissociation is just an excitation to vibrational state in which sufficient energy to break a chemical bond. Then pre-dissociation is majorly relaxation to vibrational state with sufficient energy to break a chemical bond. So the Stokes shift and the mirror image rule. So Stokes shift, a shift no longer a shift to longer wavelength between excitation and emitted radiation. Between excitation and emitted radiation. Then mirror image rule. The fluorescence emission spectrum is the mirror image of the absorption spectrum. The rule is often violated. It's always violated. So the mirror image rule is a consequence of the Franck-Condon principle. Yeah, if you remember. So basic fluorescence spectrometer. One major thing to remember is that the source of radiation is always 90 angle front facing geometry. Then we have wavelength selector, and then to the detector. That is, and this is just a sample of fluorescent spectrometer. You can be able to see the inside here. So predicting the fluorescence of molecules, some of the things that are improving fluorescence are the low energy pi to pi antibonding transitions. Then we have rigid molecules, e.g. biphenyl and fluorine, and you can be able to see biphenyl and fluorine. Then we have transitions that do not have competition. For example, fluorescence sometimes does not occur after absorption of UV wavelength because the radiation has too much energy. So dissociation occurs instead, but multi-photon excitation may be possible. Chelation to metals also improve fluorescence. Chelation to metals also improve. So inter-system crossing reduce fluorescence. Inter-system crossing always reduce fluorescence. Inter-system, because now if there is inter-system crossing, then we have phosphorescence. So some of the factors that affect fluorescence is the decrease in temperature. So if there is decrease in temperature, then there is increase in fluorescence. Increase in viscosity also increases fluorescence. pH dependence for acid-base compounds, and calculation of fluorescence using DFT, you realize that possible using modified TD-DFT approaches, we must include both vibrational and electronic calculations. So you can be able to see those. Maybe later we'll do much on these calculations. Fluorophores, two major classes. There is the intrinsic. The fluorescence occurs naturally in the molecule. The indole group in the tryptophan residues in protein absorb at 280 nanometers and emit at 340 nanometers. So you know that fluorescence and phosphorescence, they lead into longer wavelengths. Then extrinsic, the fluorophore is added to a sample. For example, 1 anilonaphthalene 6 sulfonic acid and 2 para-tulidinyl naphthalene 6-sulfonic acid fluorophores used to non-covalently label proteins. So that is where you bring a compound that is always having a chlorophore or fluorescence into a compound that is of interest. Types of extrinsic fluorescent species. We have conjugated organic molecules. We have lanthanides, component complexes, quantum dots, and nanotubes. So you can be able to see here some of these molecules that are having fluorophores. You can be able to see the likes of quinine sulfate, acridine orange, pyridine 1, and many more. There are a lot of these compounds. Quantum dots as fluorophores. So you can see quantum dots and other nanoparticle semiconductors are recent addition. And then we have cadmium, selenium, and other semiconductors exhibit strong narrow fluorophore emission with maxima controlled by particle size. You can be able to see them in form of nanometers. 12 nanometers. This one is 9.4 nanometers, 5.3 nanometers, 3.3 to 4 nanometers. This one is 2 nanometers. Very minute molecules. We have the nanotubes. Can be able to see them. Carbon and boron nitride single-walled nanotubes are currently being explored as red to near infrared fluorophores. You can be able to see them. Some of these we talked about. Quenching, a process that reduces fluorescence intensity. It's due to collision. Excited state of the molecule is deactivated by collision with another molecule in solution, and this is explained by the Stern-Volmer equation. Then static excited state intensity reduced by formation of a complex. So quenching can be done in two ways, that is collisional and static. So most common quencher is dissolved oxygen, and majorly it's unintentional. It just happens if you have your sample that is full of dissolved oxygen, then it will really affect your fluorescence. Quenching of fluorophores is commonly used to probe accessibility, e.g. by adding a quencher in varying amounts and observing its effects on a protein fluorophore to determine its location. So it's also not very bad. It can be explored for good. Time resolved fluorescence. Up to this point, we have been discussing steady state fluorescence spectroscopy. Time resolved fluorescence spectroscopy, the study of fluorescence spectra as a function of time, and demands a different experimental approach than steady state fluorescent measurements. Two major approaches: time domain. Sample is excited with a short pulse of light, and the decay in fluorescence is observed. The most common approach is time correlated single photon counting. Another approach is frequency domain. Sample is excited with amplitude modulated light, causing the emission to respond at the same frequency but delayed by the lifetime of a fluorophore. So you can be able to see them. This is time domain and this is frequency domain. So different species have different lifetimes. Here this molecule has residues in a protein in the presence of a collisional quencher shows by exponential decay. Can be able to see it. Fluorescence lifetime measurements. The latest detector allow for full emission spectra at each time point, which in turn allows for observation of excited state complex formation. Here, a dye is observed to form a charge transfer exciplex and then engages in solvent-induced relaxation. Fluorescence anisotropy. Fluorescence prefer to absorb photons with an electric field vector aligned to the electric transition moment of the fluorophore. Selective excitation of a subset of fluorophores can be achieved with polarized light, allowing the loss of polarization to be studied. Time-resolved fluorescence anisotropy is used to study protein interactions and mobility of membrane proteins. You can be able to see polarized excitation, polarized emission, and this. So resonance energy transfer or fluorescent resonance energy transfer method is possible when the emission spectrum of a fluorescent donor and the absorption spectra of an acceptor overlap. You can be able to see the resonance energy transfer effect is predicted to have a rate related to a distance r between the donor and acceptor groups. So you can be able to work it out. So this D here is the fluorescence lifetime of the donor in the absence of resonance energy transfer. Multiphoton excited fluorescence, known as MPE, as opposed to the usual photon excited. Lots of energy required achieved via femtoseconds pulse lasers. Those are the ones that can get the energy required. Multiple low energy photons can be absorbed via short-lived virtual states. Special localization is excellent because of the high energy needed. It can be confined to 1 micrometer cubic. Application primarily bioanalytical microscopy. So application of fluorescence, mostly in forensics, where we do trace level analysis of specific small molecules. Example, we have LSD, lysogenic acid diethylamide, a spectrum obtained with a Fourier transform instrument and a microscope, but with no derivatization. So you can be able to see there how we can be able to determine lysogenic acid diethylamine. Another application in biochemistry, it can be used to analyze proteins, enzymes, anything that can be tagged with a fluorophore. In some cases, an externally introduced label can be avoided. In proteins, the tryptophan, tyrosine, and phenylalanine reduces residues are naturally UV fluorescent. For example, single alpha galactosidase molecules from Escherichia coli. You can be able to see here absorption and fluorescence emission spectra of this compound, the galactosidase molecules here from Escherichia coli. It can also be used in drug discovery. The inhibition of cytochrome enzyme in an indicator is an indicator of potential drug-drug interaction and drug toxicity. Assays are needed to screen thousands of compounds for cytochrome inhibition. You can be able to see that. And fluorescence assays usually performed using plate readers are widely used. In solids, solid powders can be analyzed using powder packed behind a quartz cover slip and held in vertical position. Molecular fluorescence. Phosphorescence often used as complementary technique to fluorescence. If a molecule wants fluorescence, sometimes it will phosphorescence. Phosphorescence is generally longer wavelength than fluorescence. Some phosphorimeters are pulse source, which allows for time resolution of excited states. Pulse sources also help avoid the interference of relay scattering or fluorescence. So instrumentation similar to fluorescence, but with cooling dewars and acquisition delays. So phosphorescence studies room temperature. Phosphorescence is performed at low temperatures, 77 Kelvin, to avoid collision deactivation, which causes quenching of phosphorescence signal by absorbing molecules onto the substrate and evaporating the solvent. The Phosphorescence of the molecules can be studied without the need for low temperatures. So by trapping molecules within micelles, the same effect can be achieved. So application: nucleic acids, amino acids, enzymes, pesticides, petroleum products, and many more, where phosphorescence can be used. Then chemiluminescence, a chemical reaction that yields an electronically excited species that emits light as it returns to ground state. In its simplest form, so we have A interacting with B, then it gives us C in excited state. Then as C returns to ground state, it emits energy in form of this. You know that energy is equal to Planck's constant times velocity. So the radiation intensity depends on the rate of the chemical reaction and the quantum yield, meaning how many are chemiluminescence. So chemiluminescence of gases, chemiluminescence reactions can be used to quantitatively analyze gases, determination of nitrogen monoxide to 1 parts per billion levels. So generally, if you look at nitrogen monoxide reacting with ozone, it gives you nitrogen dioxide in an excited state. Then if you add oxygen, then you get nitrogen dioxide in excited state, giving you nitrogen in ground state plus some energy. Chemiluminescence. Luminol, a molecule that when oxidized can do many things. Representative uses of luminol: it can be used in detecting hydrogen peroxide in seawater, indicating of photoactivity. Visualizing blood strains, reaction catalyzed by hemoglobin, then detecting nitric oxide. So if you have luminol, then you have an oxidizing agent, then what you get is this energy that is in form of energy that is given out. So application of chemiluminescence: detection of arsenic in water. Chemiluminescence can be applied to fabricated microarrays on flow chip, allowing for patterned biosense applications. Electrochemiluminescence. Electrochemiluminescence species formed at electrodes undergo electron transfer reactions and produce light. Electrochemiluminescence converts electrical energy into radiation. This scheme shows both an oxidation and reduction occurs at the electrode. In most cases, a co-reactant is used so that only one electrochemical step is needed. Electrochemiluminescence, such as rubidium such a complex name, luminifor, have been the basis of wide variety of immunoassays and DNA hybridization assays. So this compound here is a luminifor. It has been very key in immunoassays and DNA hybridization assays. So further reading, you can check these particular books. Thank you. Please like and subscribe, and suggest any other topic. Thank you.